This is one of the biggest mistakes that I see data analysts and junior data scientists make. And when you do this, you can get completely the wrong answer. Specifically, I'm talking about mistaking statistical significance with causality. And I'm going to show you exactly how this can come out. First, for the full video and code, check out the website that is linked in my bio. It is completely free. Second, it's very difficult to stand out here as a niche technical creator. If you find this useful, let the TikTok algorithm know by liking, following, sharing, any sort of engaging with this post. I start by generating data. When we generate our own data, we know the exact relationship between variables because we're defining it. In this case, I have a set of products and I randomly assign them some sort of quality level. I then assign the price to be positively associated with the quality plus some random noise. And then I assign the quantity sold to be positively related to the quality, but negatively related to the price, right? So all else equal, higher quality, more people will want them, and higher price, fewer people will want them. But there's this complex relationship because higher quality products also have a higher price. Now, because we've defined the relationship between these variables, we can exactly plot out the demand curve. So in this case, products with a quality equals 100, the blue line represents exactly what the quantity sold would be at different price points. And the red dots are the actual data, but we restrict this to quality that is close to that 100 point. And you can see it generally follows that curve. But now what happens if we ignore quality? So we plot price versus quantity sold for all the products, mixing in products of varying different quality levels. And we see the relationship actually reverses. There actually looks like for higher priced items, more is sold. And if you run a simple regression of the quantity sold on price, you will get a positive impact. And it's statistically significant. And this is where so many analysts and people without a lot of experience will make mistakes. They say, oh, but it's statistically significant. That means when the price changes, in this case going up, we're going to sell more items. But you are importantly missing a key variable, and that is controlling for quality. Now, when we generated the data, we actually had a relationship that was in the natural log. And even if we correctly transform the data into logs before running the regression, we still see the effect of price is in the wrong direction. In this case, it's positive when it should be negative. Now, if we could control for quality, we end up getting the exact correct relationship with price, and that is a negative zero point 0.5 coefficient on the log. But the problem is we often don't have any sort of number that perfectly describes quality, right? It's either unobserved or it's really hard to measure. And so one thing that we try to do in this case is we look for proxies. So for example, what if we had star ratings and the star ratings, a certain proportion of them had star 1, 2, 3, 4, and 5, and those were at least reasonably related to the quality. Now, in this case, we run a regression, we have dummy variables for each of the star ratings, and you can see that the star ratings as it goes from 1 to 5, the quantity demanded gets higher, and also that the log price is directionally correct. So it's going in the right direction. It's negative, it's statistically significant, but the coefficient is still biased. It is still wrong. The effect is only about half of what the true effect is. So even with a really good proxy for quality, which is the star rating, we still don't get the exact right answer for price. And this is some of the difficulties of measuring these types of relationships when you don't have like perfect data, and it's really complex.